Hello students, welcome to Marine Engineering Tutorials. I am Atul Kumar Gupta and I am back with a new tutorial. Presently we are studying marine auxiliary systems. In this lecture we will first learn about the gland sealing arrangement provided by gland packing and mechanical seal. Next we will study the causes and effects of cavitation on centrifugal pumps. Then we will learn about the checks and maintenance required on centrifugal pumps. After that, we will study the centrifugal pump laws. Next, we will learn about the performance of centrifugal pumps. Finally, we will explore the problems associated with centrifugal pumps and remedial actions required to deal with them. Let us now go through each of these topics one by one in the following slides. Gland sealing arrangement. What is the purpose of a gland? When a shaft, spindle or rod passes through the casing of machinery, a sealing arrangement is necessary to prevent loss of working fluid. The type of sealing used depends on the operating conditions and the nature of liquid being handled. Where is the gland located? The gland is located around the shaft in rotary pumps, around the piston rod in Rasputin pumps, or around the spindle in valves. How does it seal the leakage? Sealing can be achieved either by a gland packing arrangement or by a mechanical seal, each having its own relative advantages and limitations. What are the types of gland sealing arrangements? Two arrangements are available which are used depending on operating condition and type of liquid being handled. For valves and Rasputin pumps, gland packing is generally the only option. Gland packing does not provide complete sealing but usually works with slight seepage. In some machinery, O-rings and lip seals are also employed for sealing at the gland. When leakage cannot be permitted, mechanical seal is preferred. Following slides describe these gland sealing arrangements. Gland packing arrangement. This sketch shows the gland packing arrangement used in centrifugal pumps for handling water. Throat bush retains the packing rings and restricts leakage between the rotating shaft and pump casing. The cavity formed between pump casing and rotating shaft is sealed by means of packing rings made from semi-elastic material. Packing rings can cause wear of the shaft due to friction between the two. To prevent the wear of the shaft, usually a renewable sleeve is fitted on the shaft in way of the gland packing. Heat generated by the friction can cause damage to the packing and the shaft sleeve. In most of the cases, a lantern ring is provided between packing rings which supplies pressurized working fluid for cooling and lubrication. Part of the cooling liquid returns back to the pump's low pressure site. Gland follower, tension by the studs and nuts, controls the outward leakage along the shaft. To prevent burning of the packing rings, slight leakage should be allowed. If leakage cannot be permitted due to corrosive or explosive nature of liquid, mechanical seal is used. Gland packing is comparatively simple and cheaper arrangement than mechanical seal, but it is not capable of arresting complete leakage. Removal of the gland packing can be done without dismantling the pump unless the shaft sleeve is badly worn out and requires its machining or renewal. Mechanical seal arrangement. This test shows the mechanical seal arrangement which is used when leakage is undesirable or gland packing is unsuitable due to high pressure. In a mechanical seal, primary seal is formed by a rotary and a stationary piece which are held perpendicular to the drive shaft and consist of two highly polished surfaces of dissimilar material to reduce the friction between them. Both parts of primary seal are kept pressed by a spring, which make a close contact and form a liquid tight seal between them. Stationary piece of the primary seal made up of the polished carbon ring is secured by a pin in the gland cover. Both rotary and stationary parts of primary seal are equipped with a secondary seal made up of rubber or neoprene rings. A collar is fixed to the shaft which ensures that the rotating element remains in close contact with the stationary element under the action of spring. A fiber gasket is inserted between the pump casing and gland cover, which act as a secondary seal to prevent leakage. Cooling and lubrication are must for proper operation of the mechanical seal, which takes away the heat and wear particles. Cooling liquid is supplied from the pump delivery side, which is returned back to the suction site. Mechanical seal arrangement is relatively costlier and requires removal of either the pump or its coupling and the motor for its replacement. If operated with care, it has long service life as compared to gland packing. Causes and effect of cavitation. What is cavitation? Cavitation is the formation and subsequent collapse of vapor bubbles in the pump. A vapor cavity of this type is likely to cause loss of suction or erratic pump operation. When the vapor bubbles collapse rapidly, they can remove metal from the internal wall of the pump casing or impeller and leave indent marks appearing like hammer blows. When does cavitation occur? Cavitation occurs when liquid's absolute pressure falls below the liquid's vapor pressure. During the operation of centrifugal pump, if the drop in suction pressure is greater than the vapor pressure of the liquid at pumping temperature, then vapor will be drawn from the liquid in this area. Why does cavitation occur? Cavitation is likely to occur when there is restriction in the suction pipe. Liquid is volatile or its temperature is high, or the pump speed or its flow exceeds the design capacity. This problem also occurs when NPSH required by the pump just matches the NPSH available from the system. What is the effect of cavitation? The vapor cavities formed can cause loss of suction or unstable pump operation. Cavitation causes sudden surges in the flow and pressure at the discharge nozzle and is indicated by noise and vibration. Cavitation creates spitting marks on the impeller vanes and volute casing inner wall, which increases resistance to flow, resulting in reduced pump efficiency, premature failure of the bearings, and mechanical seal. Regular checks and maintenance of centrifugal pumps. Following checks and maintenance should be carried out for reliable and efficient operation of centrifugal pumps. Regular checks. Noise, vibration, leakage, suction and delivery pressures of centrifugal pump should be carefully monitored for its reliable operation. Every 3 months. Excessive leakage from gland packing should be nipped in. If it does not help, gland packing or shaft sleeve may be renewed. Grease in the ball bearings should be renewed every 3 months. At the same time, coupling bolts and bushes should be inspected for wear and replaced when required. Check the flow of the cooling liquid for gland packing or mechanical seal through the supply pipe. Every 6 months. Performance test of the pump should be carried out every 6 months. When the performance of the centrifugal pump drops below 90%, an inspection becomes necessary and wear rings may require replacement. Every 18 to 30 months. Usually, a seawater pump requires inspection every 18 months, whereas a freshwater pump may be inspected after 30 months. During this inspection, wear rings, mechanical seal, shaft sleeve, line bearing, etc. may be renewed depending on their condition. Centrifugal pump loss. For a constant speed pump. Centrifugal pump on earlier ships were usually operated with constant speed, electric motors. Flow, head, and power characteristics of centrifugal pumps have direct relationship with the impeller diameter as described here. A standard casing of centrifugal pump can accommodate impellers of different sizes, which helps in selecting the right pump to match with the system requirement. Flow Q is proportional to diameter D. The flow Q varies directly with the impeller diameter D. Head H is proportional to square of the diameter or D square. The head developed by the pump varies directly as the square of the impeller diameter. Power P is proportional to flow Q into head H. As power required by the pump varies directly as the product of flow Q and head H, the power required by the pump directly varies as the cube of the impeller diameter. for a variable speed pump. Large seawater pumps requiring variable flow rate on modern ships are operated with variable speed electric motor as the flow Q, head H and power P of centrifugal pumps have direct relationship with speed of the pump as described here. Flow Q is proportional to speed N. For pump flow rate Q varies directly with the pump speed N. Head H is proportional to square of the speed, that is N square. Head H developed by the pump varies directly as the square of the pump speed. Power P is proportional to flow Q into head H. As power required by the pump varies directly as the product of flow Q and head H, power P varies as the cube of the pump speed. Performance of centrifugal pumps. This sketch shows the performance curves of centrifugal pump and the relationship between head, efficiency, power and NPSs required with respect to flow. Theoretical relationship between the head H and the flow Q is a straight line with minimum flow occurring when the head is maximum. Due to shock and eddy caused by the varying impeller blade thickness and other mechanical considerations, there is some head loss slightly decreasing with the flow, which is called shock and eddy loss. Contact of the liquid with the pump casing causes the frictional loss, which gradually increases with the increase in flow. Shock and eddy loss together with frictional loss changes the theoretical straight line HQ curve to the actual as shown in the figure. Actual discharge characteristics for a pump is obtained by measuring flow Q against the head H during a test at constant speed. It provides important information for the pumping system, designer and operating personnel. Reason for low rate of discharge by a centrifugal pump is due to large head requirement caused by a restricted line, very long discharge pipe, high viscosity of the liquid or discharging to a high level. Performance curves also show relationship of the efficiency with flow. Pump is designed to operate at best efficiency point with corresponding head and flow. From the curve, it can be observed that power absorbed by the pump has a straight line relationship with flow. Pump consumes minimum power with closed discharge valve when there is no flow. Centrifugal pump is thus always started with closed discharge valve, which helps in reducing the starting torque or current of the prime mover or electric motor. As the pump's maximum pressure with discharge valve closed is moderately above the pressure at best efficiency point, centrifugal pump does not require a relief valve. Starting the pump with the discharge valve closed also helps to prevent the damage to the discharge line in case the pump is already primed, as the pressure surge thus generated can create a shock wave in the delivery line, resulting in rupture of the peak section. Net positive suction head required up to the design point gradually increases with flow, after which the rise is very rapid. Specific problems of centrifugal pumps. Following problems are often encountered during the operation of centrifugal pumps, whose cause and remedial actions are discussed here. Priming failure. As centrifugal pumps can't handle vapors, it becomes a major drawback with them in comparison to other types of pumps. Priming failure is caused by lack of NPSH availability, which may be due to high frictional resistance or high velocity of the liquid in suction pipe or high vapor pressure of the liquid. To reduce the frictional resistance, suction pipe should have large diameter with smooth internal surface and short length. In addition, it should have minimum of obstructions such as bends and fittings to have clear passage. Large suction pipe diameter used is also helpful in reducing the velocity of the liquid. If possible, vapor pressure of the liquid may be reduced by cooling. In order to eliminate the difficulty of priming, centrifugal pump should be submerged in liquid, as in case of product and chemical tankers, or lubricating oil pump for main engine on motor ships. If this is not possible, centrifugal pump can be equipped with an attached priming pump, as in case of emergency fire pump or emergency built injection pump. If the centrifugal pump is required to handle low flash point or volatile liquid, it should be equipped with a wax strip system as arranged on conventional oil tankers. A foot valve equipped at the bottom of the suction pipe can help in preventing the drainage of the liquid from the pump casing. Failure of delivery. Pump may fail to deliver the liquid if the availability of NPSH is equal to or less than required. The problem can be dealt by operating the pumps at low revolutions, and two or more pumps operation in parallel should be considered. Double entry pumps also reduce this trouble. Delivery of liquid may also fail if the viscosity of the liquid increases beyond pump specification. This problem may be dealt by increasing the liquid temperature and bringing down the viscosity within pump's design capacity. Pump may also fail to deliver if it experiences high back pressure due to closed valve, very long pipe, line or storage tank at very high level. This problem can be dealt by comparing the pump's performance with shop trial data. If the total head exceeds pump design head, a booster pump will be required in the delivery line. In case total head is less than design head, The problem is caused due to reduced capacity and the pump will require overhauling. Reduced capacity. Cause of the reduced capacity may be due to high viscosity of liquid. Viscosity of liquid should be brought within the pump design capacity by raising the temperature. Cause of reduced capacity may be due to low pump speed. Pump should be operated at rated speed and the reason for low speed must be investigated. Cause of reduced capacity may be due to increased internal leakage. Inspect pump internal and measure wear ring clearance. Replace if found excessive. Cause of reduced capacity may be due to increase in internal resistance. If pump casing and impeller have indent marks, remove parts and operate pump without cavitation. Excessive vibrations. Cause of excessive vibration may be misalignment of pump and motor shafts. Check pump motor shaft alignment and correct if necessary. Cause of excessive vibration may be worn out coupling pad or bushes and bolts. Inspect the condition of coupling and change the parts as required. Cause of the excessive vibration may be loose or worn out internal parts or rotor touching with casing. Dismantle the pump and check for any loose or worn out parts such as bearings, wear rings, etc. and assemble them correctly. Cause of the excessive vibration may be the pump operation under cavitation. Check pump suction side to rule out any cause for cavitation. Motor overload. Cause of the motor overload may be due to higher density or viscosity of pumped liquid. Viscosity can be reduced by heating, which can also reduce density to some extent. Otherwise, pump should be operated with reduced flow. Pump operation under excessive vibration can overload the motor, which may be due to misalignment of the pump and motor shaft, which should be checked. Loose or worn out parts should be checked by carrying out pump's internal inspection. Check the pump's operating condition to avoid cavitation. Motor may get overloaded due to problem in the winding such as single facing, short circuit, etc. Stuck rotor, incorrectly set or defective overload relay. This completes the study of gland sealing arrangement by gland packing and mechanical seal. Causes and effect of cavitation, checks and maintenance on centrifugal pumps, centrifugal pump loss, performance of centrifugal pumps, and specific problems of centrifugal pumps. This book has been written by me and covers all the topics as per the Indian Maritime University syllabus. It explains key concepts using simple illustrations. The book also includes answers to all the questions that have appeared in examination conducted by Indian Maritime University. I am sure that the book will help students prepare effectively for exams and also support them in working safely with marine auxiliary systems. I hope you enjoyed the lecture. Feel free to share your feedback in the comment section. If you found the tutorial helpful, consider sharing it with your friends. Subscribe to the channel to stay updated with the upcoming tutorials. I'll be back soon with a new lecture. Thank you for watching till the end.